Good morning. My name is Myra Myers, and along with my peers, Anna De Leon, Kayla Oden, and Samuel Severa, we are Team One, and today we present to you our 3-minute thesis on our final project for engineering practicum. Just to give you a brief overview of what you can expect, today in this video we will be discussing a background on propellers, give an insight on our design intent, speak on our scale-up manufacturing process, and conclude with some final remarks and recommendations. The focus of this project was to design a propeller taking into consideration the decisions that need to be made at an early stage of the design so that the final product performs to the expected standards. The first version of the propeller derived from a rotating screw that ancient civilizations used to lift water from wells. In the mid-1700s, inventors used the rotating screw design to propel ships through water, but it wasn't until 1852 when Jules Henry invented the first full-size power airship which used a 3-blade propeller. Fast forward to 1903, the Wright brothers were able to create the first successful airplane propeller. Today, we have different types of propellers for different types of airplanes and boats. Modern propellers are made from aluminum or composite materials and range from 2 to 6 blades. The most common one today is the constant speed propeller, which offers better performance and fuel efficiency. Now we're going to get into more of our design intent. So the design considered different variables, including the size of the outer diameter, the number of blades, material selection, and pitch angle. These parameters were determined to have a major impact on the performance of the propellers. The main goal for this project was to produce a great amount of thrust by ensuring efficiency. To the right, you can see a CTQ tree. This was done to visualize customer needs into performance requirements. These requirements were highly considered when designing the propellers. So getting into the specifics of our design, our team wanted to create a good distribution of thrust and keep the propeller balanced. This is done by using a high number of blades. Considering this, we made our initial design with 5 blades, which produced a great amount of thrust, greater than 1,000 newtons, but it had a low efficiency. The design was also aesthetically pleasant, but it had a diameter greater than 13.3 inches and a very high mass. Looking at how 5 blades produced great thrust, our team decided to keep the propeller with 5 blades for the final design and change the geometry of the blades to reduce the mass. To compensate efficiency, the propeller was scaled using the formula shown on the screen. D2 corresponds to the maximum diameter allowed for the design, which was 13.3 inches. And according to this formula, we can state that the diameter reduction by 20% is necessary for the 2 to 5 number of blade changes. The major difference between our initial design and our final design are the shape of the blades. The blades of the initial design are rounded, and the blades of our final design have a triangular shape and are narrower in order to reduce the mass. After designing the propeller, the next step was to perform a flow simulation using SolidWorks to calculate the ability to produce thrust. The new design produced a thrust of approximately 940 newtons. The only concern is that the air flows in but does not flow out of the propeller. The exact cause of this behavior is unknown, but our team recognizes that factors such as blade geometry, blade dimensions, and pitch angle should be examined to improve the performance. In terms of material selection, the team wanted to use a lightweight and more resistant material than ABS that could be implemented in additive manufacturing. Kevlar has been the most promising due to its excellent strength-to-weight ratio. 3D printed Kevlar is 3 times stronger and 12 times more rigid than ABS. Kevlar also has some benefits when it comes to 3D printing, including cheap replacements for manufactured parts and smooth print due to its long and regular molecular structure. For a hypothetical scale manufacturing, we think the most suitable layout would be having the printers placed in a U shape, followed by an I-shaped line. The U shape will facilitate travel from one printer to another. No skilled machinists are needed, so labor costs are lower. Only retooling and starting the printing process are required. After printing, the parts will be removed from the printer and then transferred to the I-shaped line to be post-processed. The post-processing methods include sanding and painting. There will be no limitations in blade geometry. Each propeller model and quantity will be printed per period, whether it's hours or days, depending on the demand. The production line can be adapted. However, changes in printing speed or material may change the quality of the product. Therefore, a balance between quality and speed should be made. All in all, the goal of our final project was to design and manufacture a propeller using the tools that we learned in previous IME courses and the refined techniques learned in this course. Moving forward, the team will focus our redesign on blade geometry, blade dimensions, and pitch angle. The next step will then be to focus on CAE. This will be completed by finalizing a functional model of the design and evaluating it in terms of flow of air, thrust, and weight. Next, we will conduct virtual prototyping by building the same design in several programs and conducting the same evaluations to analyze the similarities and differences. Lastly, we will use additive manufacturing to build a physical model of the propeller, where this propeller will also undergo a series of tests. This concludes our 3 minutes thesis, and we thank you for tuning in.